Hi, this video is about Riemann sums and definite integrals. Just as a warning for you, we're not going to be really concerned about the calculations in this video. Mostly what we care about is like conceptually what's going on so we can get an idea of what a definite integral is trying to create. So there are two types of integrals, definite and indefinite. Definite have a start and an end. You can see you got the 0 and the 2, while indefinite are more general. You can think about these as when we found the derivative at a single point versus finding the derivative of the whole thing. Definite integrals are like finding the derivative at a single point. It spits out a number, while an indefinite integral takes the antiderivative of a whole function and kind of undoes this idea of derivative. But this video is just about definite integrals. We can estimate a definite integral using rectangles. So we can get an upper and lower by like breaking it up into pieces, adding up all our heights and multiplying it by the width of those rectangles. But as you can see with this upper and lower estimates, it's wildly different. So trying to find a way to be more accurate kind of calls for us to make more rectangles. So we need a way of adding a whole bunch of numbers together, which is the summation notation. So this is a sigma. It's a way of representing a whole bunch of numbers being added together. We need to know what this is just for notation's sake. We don't need to actually calculate any of these, but we need to be able to recognize what's going on with this sigma notation. So it is saying we're going to sum up a bunch of a's. So we'll start with 1, and then we'll go up by ones until we reach this upper bound. So we've got a sub 2, then a sub 3, then a sub 4, 5, 6, 7, etc., until we reach some a sub n. There are some additional formulas down here. We're not really concerned about those formulas. The one I want you to focus on and know about is this one, where if we have a constant inside of a sigma, we're able to pull that out in front of our sigma, which is kind of what we did with these. All of these were being multiplied by 2, so we could just pull out that 2, add separately, and then multiply by 2 on the end. So I did this one off to the side. We don't really care about figuring out the sigma thing and like how we get to this green thing, but I did it for us just so we can get an idea of like, okay, what is going to happen? And then we can check what happens if we do this 10 times. So we have this be 1, then 2, then 3, then 4, then 5, etc. Rather than actually adding all those together, we can just do this calculation over here in green. And what we end up getting is 4.25. But then I'm curious because, again, we're thinking about like adding a whole bunch of rectangles together. What if we did more rectangles? What if we had 100 rectangles? This isn't actually making rectangles, but what's happening as we add something more and more and more? Well, if we put in 100, I find out that, okay, well, it's changing a little bit. It actually went down our sum because we're dividing by a bigger number. So, okay. So it's changing to this 3.57. So it changed pretty significantly from that 10 to 100. Well, what happens if we go even farther? What if we go to 1,000? If we plug in 1,000, and I just did that off to the side, I got 3.5075. So it didn't change as much when I did a 10 times more n. So it didn't really change all that much. It's about the same thing. There was a big jump and then not much of a jump. And then if we tried 10,000, it changes even less. It's not very different from where it was before. So we notice in these summations that as this n value gets really, really large, then things seem to calm down. So if we can get a huge number in there, we should get to a fixed point. This is not just going to continually grow. Those are the summations that we're going to be coming across. So we want to apply this idea of summation to rectangles, because if we can get a lot of rectangles, we can get a really accurate idea of what this definite integral would be. So we're going to use this delta x to represent the width of our rectangle. So that's how wide each one's going to be. That is a constant. And as we were talking about earlier with that summation, if you've got a constant, you kind of put that in front. That thing that all of the heights are being multiplied by, put it in front. And then here I'm trying to figure out what our midpoint is. So it's between our first x and our second x, and then halfway between those two, plugging that into our original function f. And we got to add all of those things together. So that's why we've got the summation. So this would be the same idea, but done with trapezoids. We need a 1/2 that goes in front because that's going to get multiplied by all of our heights. The width of our trapezoids, and then we've got our left and our right hand side of our trapezoids. That is our B1 and our B2. So we're just adding those two together and then summing all the things that we're coming up with. So this is the definition of a definite integral. Once we start getting an infinite number of rectangles, then we are going to perfectly describe that area underneath our curve. It can be tough to understand what's exactly going on here. So let's look at this delta xi. This is trying to represent the width of our rectangles, because as you can see, as we go along, we get thinner and thinner rectangles. So this is getting smaller and smaller. You can also do this with rectangles of different widths. So some rectangles being wide, some being narrow. That's why we have this x sub I. But we're going to assume that all of our rectangles are that same width so we can see what's going on. If we have a constant inside of a summation, we can pull that constant we can pull that constant out of the summation. So it can just chill right here. And then we can kind of see, there's our sum of all of our heights. But is our limit going to manipulate with that? No, because if you take the limit of a constant, that constant stays the same. So here you can see we're keeping those rectangle widths all the same height, the rectangle widths all the same, and then multiplying that by an infinite sum of rectangles. We need that infinite number of heights as we move from point to point to point all the way across. So we can get our rectangles basically a thin line rather than a full rectangle. And that tells us the value of our definite integral. Let's apply this definition to an actual formula. So if we wanted a definite integral that yields the area of the region bounded by the curve and the x-axis, so we're trying to figure out what is this region in here, we would want to see what's going on from -5 to 5. So this is the integral from -5 to 5 of our function f of x. And then on the end, we always do dx because we're the width of our rectangles is going across the x-axis. So it's also kind of telling us what we're finding the antiderivative with respect to. We always have to put that little dx there. We can write this using that definition as well. So, we could replace that with our actual function. So that's -5 to 5 of 25 minus x squared dx. This should probably be in parentheses there. But if we were to write that with our limit definition of this, it would be the limit as n approaches infinity, because we need an infinite number of rectangles. We need a summation. We're going to start with I at 1, because we're going to go from one rectangle to an infinite number of rectangles. And then we need our function. So that is going to be our 25 minus, we're going to use c sub I for our x because we're going to put in different heights along the way. And then we're going to square that thing. And then we need our delta x sub I. So that's going to be talking about the width of our rectangle. You can see how this delta x sub I is matching up with that dx. So that's talking about how wide our rectangles are. D stands for delta, triangle stands for delta. There's a video that exists where I do that by hand. Don't worry about it. Don't watch it. Don't watch it. It exists, but I wouldn't recommend watching it because you don't need to do it. And so I wouldn't watch it, but it exists. That is the end of our video on definite and indefinite integrals. Again, a definite integral has a start and an end. Think about it as finding the derivative at a point. This is finding the antiderivative for a definite part, finding the area under a definite part of our curve. An indefinite integral doesn't have a start and an end. It's more like just finding the derivative of the whole function. This is our formal definition of finding that definite integral. You don't need to be able to do this. It's not tested. You do need to be able to recognize this as a definite integral and being able to just do this instead. And we'll talk more about how to do that in another video. Thanks for watching. I hope you took good notes on the things that I was saying, and I'll catch you later. Bye-bye.